Okay, so now that we know that matter has wave-like properties and that we can use the de Broglie wavelength or de Broglie wavelength to calculate the wavelength of matter depending on its momentum, how did we find definitive proof that that theory is actually true? So a great experiment called the Davison-Germer experiment was performed where they accelerated electrons using an electron gun. Okay, I can change the speed of electrons. We've used this apparatus before in the nuclear physics unit and in the classroom. And so if I change the voltage, I can change the speed or the momentum of electrons going through a beam. And then that beam can be targeted to a very thin material, such as a thin layer of graphite. And that electron beam, which has wave-like properties, is going to be scattered or go through that material. And if it goes through in between the spaces of atoms, it will diffract. The atoms themselves will behave like a diffraction grating or have these spaces, these apertures for those waves to go through. And if that spacing is on the same size as the wavelength of matter, we get maximum diffraction. So if you remember in our previous calculation, okay, the wavelengths were around 10 to the minus 10 meters. So if the spacing between atoms is around 10 to the minus 10 meters, we would expect that these electrons should diffract through that material. So I could use this diffraction equation to be able to calculate things such as the spacing between atoms, that would be d, or the wavelength of matter if I measured the angle of diffraction. Now it's important to know that when that wave is going through this material, it's a single wave, single beam, and that beam is going through a single hole. So this would be single slit diffraction. So that theta should be actually measuring the minimum, the deconstructive interference. So when you see 2 theta over here, they're looking at constructive interference. I have to multiply that by 2. So just important to know that this formula, when it's electron diffraction, is for single slit diffraction going through a single hole. So let's see if we can put that to practice, okay? So in the Davison-Germer experiment, they weren't going through a thin material. They were scattering light off of crystals. And you'd still get diffraction. When that light goes through that first layer, it's going to diffract and reflect off. They had a detector that they could move around at angles. Okay, so if I start at 90-degree angle, I'm just measuring reflection. And as I slowly move that detector down, the first angle that I pick up, like a maximum, would be here. And then that'd be my second maximum. And you can see that graph over here. So the detector would start at 0. And as they moved the detector away from 0, I'm getting less and less intense beams. Here would be my deconstructive interference. That would be deconstructive interference. And then here would be my first constructive interference. That would be my first max. Okay, so if we're using the equation d sine theta equals n lambda for single slit interference, what we're looking at, let's just change the color of that. What we're looking at is our first minimum. Okay, so that's our first minimum. That's where we get destructive interference. So the first minimum on this graph is appearing at 30 degrees. Okay, so they would use this data, and if they knew the speed and the momentum of the electron, they'd use this data, the wavelength of the electron, to calculate the width of atoms in a nickel crystal. Okay, and we're going to try to practice that calculation right now. So let's take a look at this voltage. So if my accelerating voltage, let's change the color. If my accelerating voltage was 54 volts, so if I had 54 volts as my accelerating voltage, what would be the wavelength of that electron? So what would be the wavelength? You can try to stop that right now and see if you can do the calculations from what we learned before with the de Broglie wavelength. But we can move on right now. So voltage times the charge of an electron is equal to kinetic energy. Okay, that's the first step that I need to know. So 54 volts times 1.6 times 10 to the minus 19 coulombs is equal to the kinetic energy of an electron. And we know that the kinetic energy of an electron is equal to 1/2 p squared over m. Okay, and then the wavelength is equal to h over p, which we did in the past was going to be h over the square root 2 KEM. Okay, so if I go back in here, I found my kinetic energy, and if I plug that in over here, and I know the mass, if I know the mass of the electron, okay, okay, 9.11, and I know Planck's constant, I'll be able to solve for the de Broglie wavelength of that electron when it's accelerated at a voltage of 54 volts. And that de Broglie wavelength happens to be, for this situation, 1.67 times 10 to the minus 10 meters. Okay, so if you go back and work this out, okay, I have my kinetic energy, plug it in here, the mass of the electron times 2 square rooted, Planck's constant divided by all of that would give you the de Broglie wavelength. Okay, now how can we apply that de Broglie wavelength? We're going to do that in the next problem. So using the wavelength and graph to calculate the diameter of the nickel atom here, okay, our minimum was 30 degrees, so I can use the equation d sine theta is equal to n lambda, and that would be, n in this case is going to be 1 because that's our first order minimum. So n is going to be 1. Lambda, we just calculated. Okay, the angle that we're looking at is 30 degrees because that's the first order minimum. So in this case, d is equal to n lambda over sine theta, which is going to be equal to 1.67 times 10 to the minus 10 meters divided by sine of 30 degrees, which, if I work that out, will be equal to roughly around 3.3 times 10 to the minus 10 meters. Okay, so in that case, the diameter of a nickel atom, if this was all true, if this really does relate to that, the diameter of a nickel atom, according to our experiment, is around 3 times 10 to the minus 10 meters. And that is close because the diameter of atoms are on the order of magnitude of 10 to the minus 10 meters. So I know that my answer makes a lot of sense. Okay, so that was a really important experiment. Just to summarize, we know that matter behaves like waves because when I shine a fast enough electron beam at matter, it diffracts. And diffraction is a wave-like property. We see a diffraction pattern. So that's proof that matter can behave like waves. All right, and the application of this is I can use a matter wave to measure the size of something small, such as the diameter of an atom, using the diffraction equation. Okay, this would be an excellent problem on an exam where they give you like a voltage here. You have to calculate the wavelength of a beam and you have to use a graph to measure the width of an atom. That sounds like a really good 10-mark question. All right,